So I know you guys have a few problems unfinished from the previous homework, but I thought it might be better for me to finish off pretty much everything in the syllabus today, both the classes, so that those few problems that you had and the two problem sets you can do on the entire day for Wednesday. So I think that way, yeah. Yeah, so maybe we can start at 10 if that's okay with all of you. Yeah. So,
class tomorrow?
no class tomorrow.
Class tomorrow, Wednesday, 10.
Yeah. We'll try to wind up by lunch because we have to go to that other place. 3:30 is just about a half an hour walk. But in case we are not able to do it by lunch, maybe we'll do for half an hour or so after the lunch as well. Okay, it's been a while since we had any lectures, but I think the last one that slide that I left you with is when I introduced this concept of the addition of the angular velocities. And this is the case irrespective of whether you have simple rotations or not. But when it is simple rotations, it becomes a very useful tool to have, because typically you are talking of two systems which are having very complicated motion relative to each other. One might be static, it could be an inertial frame. The other could be the aircraft fixed frame. And that can typically kind of be broken into smaller parts, each of which could be a simple rotation, for which of course you need to introduce a so-called intermediate frame of reference, which in this example we called as C. So with this intermediate frame of reference, then you're essentially going from frame A to C and then from C to B to get to the body that we are interested in studying the motion of, right? So this is common to determine the angular velocity as a sum, and this is just an example where one intermediate frame has been introduced. Therefore, you just have two angular velocities, but you could have as many as you like for a particular problem, depending on its complexity. Okay, so differentiation in two frames of reference is one place where you would have the advantage of. Is there some carpet or something? No. So there's some water spilt over here. That's why. Yeah. While the angular velocity by itself is a great kinematic feature, the advantage of having something like the angular velocity as a concept goes beyond just the idea of studying the speed of that angular motion or rotational motion of a body. It can be used for various other purposes, and in fact you've seen a few examples of that already. One of course is differentiation in two frames of reference. It might be easier for you to differentiate in one particular frame of reference, but you might want the derivative actually in a different frame of reference. So instead of going to the basic definition of that derivative, you take advantage of the concept of angular velocity, and you just add a term to the derivative in the frame that it's easy to take the derivative, and then lo and behold you have the derivative in the frame that you are interested in. For example, any arbitrary vector q, if you take up, then its derivative typically is required, for example, in an inertial frame of reference, which may not be. It could be any particular frame of reference that you are interested in. Then suppose you already have its derivative in a particular frame. In some cases it could even be 0. We'll see that example as well. In which case you see that all that you need to do is to that derivative you add a term which is just the angular velocity crossed with q, where the angular velocity in question is between those two frames of interest. So in this case you have A and I. So you have two frames of interest A and I. So essentially you're trying to make sure that your angular velocity there, which might again be either a simple rotation or it might be a sum of simple rotations like what we saw in the previous slide. You take advantage of that, and then you go on to cross it with that arbitrary vector in order to get the derivative in the new frame of reference, or the frame in which it was difficult to take the derivative otherwise. Okay, now coming to examples of Q. As I said, it's an arbitrary vector. So some examples that we typically encounter in dynamics is for Q to be either the displacement velocity or acceleration, the angular velocity, etc. Acceleration, of course, if you're interested in studying impact mechanics and going to jerk and higher order derivatives, but otherwise it's usually displacement velocity and angular velocity to get to angular acceleration, right? So now it's a very important relation, of course, used quite frequently, as you will encounter in your remaining homeworks as well. And this angular velocity is therefore key to the differentiation of vectors in rotating frames of reference, because there's no restriction, remember, in the frames I and A we have talked about over here. Even though I'm using an inertial frame of reference, as I said, it could be any arbitrary frame of reference as well, the combination. And therefore, these could be not only accelerating with respect to each other, but also rotating with respect to each other, in which case automatically there is an acceleration. But essentially, you're seeing that the wide possibilities of utilizing this particular equation of a q dot in I being a q dot in A plus the sum of cross product. Okay. So in addition to, of course, the primary purpose of the angular velocity is always to steady the angular motion of a particular rigid body in a particular frame of reference. But in addition, it serves these purposes of simplifying our derivations quite a bit. Okay. The simplest case is when the d by dt of q, that is q dot in A, is 0. For example, it could be a vector which is, let's say A is the aircraft and q is fixed on the aircraft, and then you want to study the change of that in inertial frame of reference, then you don't even need to take a derivative. All you need to do is a cross product, which means that essentially you're solving a differential calculus problem by just using a linear algebra, vector algebra that you have. So you see the link between calculus and algebra over here, which is phenomenal. It might look innocuous, very simple equation, but how much it simplifies our tasks, you get to know only when you actually solve problems. So coming to angular acceleration, again, this is a concept that we have known earlier, but we want to see in the context of what we have just introduced for angular velocity, can we do something similar with respect to angular acceleration as well? So suppose we have two frames of reference, let's call them as A and B, and you want the angular acceleration of one of them in the other, let's say B in A, then you know that it's very similar to the translational acceleration being the derivative of the translational velocity. Here the angular acceleration is the derivative of the angular velocity. But one very interesting thing that we will see as at the end of this slide is as far as this particular derivative is concerned, it really doesn't matter whether you take the derivative in A or B, okay? Which is something that we've been harping on. Remember, it's very important to specify the frame of reference. Yes, it is, but there are some special cases where in two different frames you might have the same value, and that's very easy to see from the result that we had in the previous slide, where we had that cross product between omega and the vector, which is what we will use here, because the vector of interest now whose derivative you're taking is omega itself. So an omega cross omega is nothing but a vector crossed with itself, which means they are parallel to each other, and therefore the cross product will go to 0 because the angle between them is 0, and sine theta is involved, the sine of the angle between those two vectors, and therefore it really doesn't matter as long as you're looking at the angular acceleration of one body in another body or frame of reference. These two terms or phrases can be interchangeably used, rigid body and frames of reference. Then the angular velocity that you have to take the derivative of could be in the derivative could be in any frame of reference of amongst those two. Obviously, you can't say I'll choose another frame C and take the derivative. That's not going to work out for you, right? So, in general. So, coming to utilizing that equation in the previous slide where we had Q in the place of Q, we are taking a special example where we, instead of Q, we are putting it as the angular velocity of B in A. And when we do that, we see this is the equation that we get. So these are the two places on the right hand side where Q was there, and so we have substituted it as omega BA. This was already omega BA in the general equation itself, okay? But the speciality of this particular choice of Q amongst all the arbitrary vectors that you can have is the fact that you get the cross product of the vector with itself. Okay, so which means that therefore, as I said, because only this term remains on the right hand side, so if you just compare these two, you see that the omega dot of b slash a is the same whether it's taken in frame A or taken in frame B. Okay, so to calculate the angular, because sometimes remember that the angular velocities, just like any other vectors, when you're using it for calculations or derivations, it might be expressed in a particular frame of reference in terms of its components or measure numbers. So if you already have it in B, you don't need to convert it into A system and then take the derivative. You can directly take the derivative in the B system itself, because B1, B2, B3, the hats, the unit vectors will be fixed, and therefore they will not have a time derivative. Only the measure numbers you need to take the derivatives of. So that becomes much simpler to do than going all the way around to conversions and etc. It's not that it's impossible, it just saves you a lot of time and effort, makes things much simpler. So to calculate the angular acceleration of B in A, we differentiate the velocity of B in A in either frame of reference amongst those two only, okay, nothing else, but that itself is a great choice to have. Otherwise we were fixated on a particular choice, single choice. Now we have at least two options, and to choose whichever is simpler to take the derivative with respect to. So usually the usual differentiation formula to differentiate angular velocity in all other frames of reference. So now we saw at the end of the previous lecture as well as at the beginning of today's lecture that angular velocities are additive in nature. In other words, you can introduce intermediate frames and then you can go on adding in a sequence going from one frame to the other. But the same thing cannot be extended to angular acceleration. It's very important for you to remember that. So in other words, if I have two frames A and B and I introduce the frame C in between them, then I cannot just take this term going from A to C and C to B. I will get A to B, which is what we said in the case of angular velocity, and that was absolutely right. But in the case of angular acceleration, it's not so, because you have an additional term to deal with. Why is it so? We can very easily verify that from the knowledge that we already have. So let's see how this particular additional term comes up. You have the angular velocity of B in A, or any angular velocity for that matter, is additive in nature if you introduce an intermediate frame C over here. That could be an actual body, or it could be just an imaginary thing, a figurative thing, which helps you to make this transition of a complex rotation between the two by introducing relatively simpler rotations between them, which in fact might be the simple rotations that we have introduced as a concept as well. Okay, whether they are or they are not simple rotation doesn't matter, that's always valid. Now if we want to get from this to the acceleration, which is what we want in the left hand side of this equation, instead of omega b slash a, I want alpha b slash a, and for that I go to the basic definition of the angular acceleration in terms of the angular velocity as a time derivative in the particular frame of reference A. Now of course I know that it doesn't matter whether I take it in A or B, which is what we found from the previous slide, but this is the basic definition. Okay, so now, because I can substitute for omega b slash a using the first equation in green font on the top into the yellow, then I get instead of the sum, taking the derivative of the sum, I'm taking the sum of the derivatives, which we know is a property for just like for scalars, for vectors as well. Okay, now each of these we are essentially looking at taking I'm keeping the last term as it is, the first term b slash c. We are using that general result that we got for any arbitrary vector. If you want to take in one particular frame, you can take in any other frame and just add the term which is a cross product of the angular velocity of those two frames, namely c and a, which is why you say c slash a, and of the vector whose derivative you are interested in, which is b slash c, which is why the second term in the cross product is a b slash c. Okay, the last term is retained as it is, d by dt of omega c slash a in A, that is retained as it is. It's only the first term to which we have applied that formula that we had. Okay, Now you see in this particular thing that you have these two are nothing but the derivatives of the angular acceleration, okay, of the appropriate body in the appropriate case. So here it is of angular acceleration of B in C, and this is the angular acceleration of C in A. So we get those first two terms as anticipated, but this doesn't go to 0 like what it did earlier, because earlier we had both these as the same and therefore they were parallel to each other, and sine of the angle between them is 0, and therefore they that was going to 0. But now one is C slash A, the other is B slash C, and in general they need not be parallel to each other, which means you will be left with this additional term, which means that the addition theorem for angular acceleration is not valid. Yes, we have those two terms, but we have something in addition as well, which is what this cross product of the two angular velocities are. Okay, so this formula is also actually useful. Many a times we might know these two accelerations more easily compared to that. So we can take advantage of this, and this cross product is usually not so difficult to evaluate. So you can add that, but just be aware that there is this additional term that you need to take care of. Okay, so now a few notes on the notation, because I've been stressing throughout the course, be very precise, introduce the inertial frame of reference. Whenever you're taking a derivative with respect to t or s, you, or any scalar for that matter, you put the frame of reference as a pre, postscript, etc. Pre, the superscript, etc. Yes, that's very, very important, especially in the current trend that we are having in moving towards most of this being implemented in symbolic software like Mathematica or Maple, or even rudimentary manner in MATLAB, etc. So being precise in terms of the definition really helps for the software to understand us, whereas we as human beings, even if that is not specified, we might be able to guess this is what is the frame in with respect to which we are supposed to take, and therefore if somebody leaves out also, the reader might be able to figure it out. But with the LLMs and the transition of that to mathematics, that's becoming possible to some extent with the software as well. Okay, for the software to recognize that is there are only two bodies, so it has to be one of these two, and intuitively this is the appropriate choice. So that is a direction in which things are going, but in spite of that, it's essential, at least until that kind of stabilizes and becomes concrete, for us to be more precise, so that way you avoid ambiguities of any sort. It's always helpful, especially when you're solving more and more complex problems. You already have complexity in the problem definition. Why do you want to add to it just because of your imprecise way of defining the variables? So that's the thing. But when you have simple problems like a few that are there in your homework, etc., it's okay sometimes to not include, but you have to at least orally mention what you're doing. Okay. So in such cases, you will see that sometimes the subscripts on the angular velocity might be dropped off, subscripts on the angular acceleration might be dropped off, especially if you think that it is kind of obvious, but you do have to state that in those situations. Similarly, with respect to which frame you're taking the derivative, which is essentially your left superscript on the time derivatives, or for that matter, derivatives with respect to the arc length, etc. So of the center of masses of rigid bodies, then you might sometimes drop that, but define it up front so that those are the default values for whenever there is no pre-superscript, then it means that that derivative is with respect to a particular frame. So as long as you're defining that up front, it doesn't matter. Okay. The advantage of dropping them off in simpler problems is, of course, you see that equations look more compact than they would if you have the precise definition. So it reduces not only your time and effort, but also the clutter, and in terms of visualizing those equations and inferring a lot of information from that, sometimes it helps. Okay. But more often than not, it's rather than helping you, it's going to be a disadvantage for you, because eventually you might get into confusion if you don't follow that intuitive thing throughout. So sometimes confusing, especially when you are dealing with part of the work being done by human and part of the work by a computer software. Then it could be some algorithms, or it may or may not involve AI, but which are becoming the kind of new normals. So then it's always better to go back to the more precise definitions. And For more and more complex problems, you rarely would do it everything by hand. It will be typically software, and therefore it really helps to be more precise, because there again there is so many options are there in terms of with respect to which frame you're going to take the derivative. Okay. So now having said those generic things, there are a few things that we will just revisit as a revision, because they are going to talk about another case which is useful, which is very similar to this. So therefore very quickly we will look at this particular expression or formula that we had derived one of the earlier classes for any 2 points which are fixed on a rigid body. And suppose that rigid body is moving in an arbitrary fashion. It could be having a constant speed or accelerating. Its acceleration could be constant or changing, doesn't matter. And the acceleration being non-zero essentially means either the velocity, magnitude and or direction changes, and both are allowed in this case, which means that there is a possibility of rotation as well. So when you have such a situation, we saw that if you know the velocity of one of the points fixed on the body, you could get to the velocity of another point, any other point on the body, which was a useful formula. So we'll just very quickly revise that, and you remember that, in fact, because you've utilized it so many times in your work, that these two velocities of P and Q, of course in a particular frame of reference, let's say I, are related to each other by just the difference being just a cross product of omega cross RQP. This is once again the same general formula that we introduced, where Q is replaced by the position vector RQP, and so you see that that's essentially what you're utilizing over there, right? So now this, or you can even think of it as the sum going from Q to P. You're going from, so let's say going from O to P, you're going from O to Q first and then from Q to P. So that sum essentially you can see in that fashion as well. So many different ways in which we have seen that that can be derived. So velocity of one point of a rigid body is known, therefore finding the velocity of any other point for that matter, absolutely the other points which are also of course fixed on the rigid body, is a child's play, just by adding a cross product of the angular velocity of that body on which those points are fixed with the position vector from the point that you're aware of the velocity to the point whose velocity you're not aware of, and then you essentially calculate that, right? Now for the same thing, of course, you also had the acceleration, we had the velocity, we had the acceleration as well. Accelerations are always, whether it's angular or translational, slightly more complicated compared to the velocities, but not a whole lot. So you just have one additional term that you're going to deal with. In the velocity, you had just the, on the right hand side, you had just the first term and the last term. With the alphas, instead of the alphas you had omegas, instead of A you had B. But now you have this second term, which is essentially your centripetal acceleration that you have, omega cross within brackets omega cross RQP, right? So that as long as you take care of this additional term, you are able to do that as well. This is again something we have already seen, right? So what it meant is that if the acceleration of one particular point, again I've mentioned this before as well, so there's no special treatment given to boundary points or to interior points or to points which are may not be even a material point. Okay, so that's why I say on or in or with respect to that particular rigid body. So it could be any one of those and between P and Q, one of them could be one, the other could be the other kind, doesn't matter. Okay, so as long as it's fixed with respect to the rigid body, you can utilize this formula for acceleration as well as on the previous slide the velocity formula. So find the acceleration at any other point of the same rigid body using the angular velocity and the angular acceleration, because you see that both are coming into picture. There's the angular acceleration of the body B and the angular velocities of velocity of the body B in the frame in which you want to determine those accelerations. So now we already have the equations for V and A in the previous two slides. Two slides earlier we saw V, now in just the previous slide we saw A. So we have the equations for both V and A of to relating the values of that for two arbitrary points, both of which are fixed on the rigid body, in the rigid body or with respect to the rigid body. Now we are taking a step further and looking at deriving the expression similarly for velocity and acceleration. There we didn't derive because we had already derived in a previous class. So we are just restating that to refresh our memory and to show the parallel between what we are going to do right now. Okay, what are we going to do right now? It might look simpler than what we were doing, because there we had 2 points. Now we have reduced to 1 point, but the complexity is that that particular point is not fixed, but it's moving, and moving either on the body, that's on the surface of the body, or within the body, or like a passenger within an aircraft, or with respect to the body. For example, it could be, let's say, you have another aircraft which is refueling an aircraft mid-air, and then you could be talking about let's say a particular point on that fuel hose pump or whatever, right? So all these possibilities are there. So since we have to derive it fresh, let's start as always with a frame of reference, which is inertial. This is of course kinematic, so it really doesn't matter, but because we want to get ready for eventually kinetics as well involving this problem, so therefore it helps to have it an inertial frame of reference, but it could be for any other frame of reference. Okay, then we introduce of course a coordinate system associated with it, the unit vectors associated with it, and origin associated with it. Again, this can be translating without rotating anywhere, and therefore the origin could be something else, and the distance between that new origin, let's say O star and O, is a constant, and therefore it will not be affected by any of the derivatives we take, etc. So the specific choice of O doesn't matter, because it's the relative distance that is of significance to us. Okay, so just like we did that for the frame of reference with respect to which we want to study the motion of both the body as well as the point on the body, we also introduce a frame of reference associated with the body. Okay, and this is something that you do with all problems depending on the number of bodies you have. For example, in the 4-bar mechanisms you had 3 bars, and the 4th bar being of course the ground itself, which is not. So you had 4 different frames of reference. One is the inertial frame, and 3 for the 3 bars, B1, B2, B3, and some of you solved those problems related to that. Here it's much simpler. You have only one body that you're dealing with, and for that body we introduce a frame of reference here with an origin O prime. And as I said, this is a body which is moving in general, which means its center of mass could be accelerating, and the body itself could be rotating in any arbitrary fashion. Okay, and the choice of O prime that you take usually is the center of mass, but need not be. Okay, it could be any particular point on the rigid body, but it's fixed in the rigid body because you want to fix the frame to that particular point, so the point also has to be fixed. Okay, but what we are concerned about now is the motion of another point P, which is not only moving along with the body. As the body moves, P also moves. As the body rotates, P also rotates, which would have been just the same case that we had earlier, that O prime and P are both fixed in the body. But we don't want to do that. O prime continues to be fixed, but P can move on the body, in the body, with respect to the body. And then we want to see if I know how P moves with respect to body B, can I determine how P moves with respect to the frame of reference I. So which is what this particular formula will really help us. So as always, we start with a simpler thing, which is velocity, and then we will graduate it to accelerations as well. Okay, so if point P were fixed in the frame of reference B, which is the case we had earlier, then we know that it's a very simple formula that you have, that the velocity of P in I is just the velocity of O prime in I with the other point which is fixed, and then you had to add the term which is a cross product of the angular velocity times the position vector between those 2 points, from the point whose motion you already know to the point whose motion you want to determine, which you do not know. Okay, from the unknown to the known is the direction in which we always have this position vector. Okay, so this would have been true if P were fixed. Okay, but we know that P is not fixed. P is also moving on the body. Okay, but at a given instant in time, instantaneously, I can make a mark at that particular instant of time where was P. Okay, and I mark that particular material point of the body and I give it a new name, and then based on the earlier knowledge that we have of 2 points fixed, I would know the velocity of that point. But then I can get the distance between these two, the derivative with respect to time, and then eventually get to the velocity of p. That is the strategy. Okay. So what if p moves on in the frame of reference b as well? Of course, it's moving with respect to I. What if it moves with respect to b as well, which is what we are interested in? So now, given the point p's velocity in the frame of reference b, can we find the velocity in the other frame I that we are interested in? Okay, so which is what we are going to do with this. Okay, forgive me for the smaller fonts, but I'm sure you should be able to see it. So coming to the position vector, we want to go from O to P, that is the origin of the frame with respect to which we want to eventually describe all of the motion in our kinematics, and the point whose motion we are interested in, which is P, which is also moving on B. Okay, so we want to go from O to P, so we take two steps, go from first from O to O prime, and then from O prime to P. Quite obvious, right? Because we have a frame in B, so obviously we go to its origin, which makes things simpler, because we know, for example, as I said, it could be the center of mass, and you're already aware of how the body B is moving. So you know the velocity of the center of mass, acceleration of the center of mass, etc. So we want to take advantage of that. So then, of course, we have to go from O prime to P, which is not a constant anymore. Okay. Earlier formula that we had, both O prime and P were constant, but now P is moving on B. Therefore, the second term is also changing, not only with respect to I, but also with respect to B. Okay. So now we get to the very basic definition of the velocity of P in I. That's nothing but the time derivative of the position vector from a point which is fixed in I, because we want the velocity in I. So it has to be a point which is fixed in I, which is O, an example of that. And then, of course, whose velocity we are interested in, P. So we have to go to that. So that position vector I have to take its time derivative in I. Okay, which now we know can be broken up into two parts. Because of the first equation that we have, we substitute for our OP as a sum of two position vectors, and therefore it's the time derivative of both of them in the same frame of reference I, and then I have to add them up, right? Now, if you look at the first point, O prime on the body, the position vector from O to O prime, its time derivative in I is nothing but its velocity. So I just replace this particular term with the velocity of O prime with respect to I. It's only the second term which is a little more complicated, so I will take now the advantage of that thing that we said is valid for any arbitrary vector Q. Instead of the arbitrary vector, I am using the position vector from O prime to P, and when I do that, I have to take not the derivative in I, but in the simpler frame, because we know the motion of P in B. So we take the derivative in B first, and then add a term which is a cross product of the angular velocity of B in I, because B is the body on which P is fixed, and I is with respect to which we are studying the overall motion. So therefore, that particular angular velocity, in any case, there are only two entities there. It has to be the angular velocity of one with respect to the other. Okay, so there's a cross product, then of course with whose derivative we are interested in, which is your position vector from O prime to P. Okay, now we can simplify this thing because we know that the first term within the bracket is essentially nothing but a definition of the velocity of P in B. Okay, because we are taking the derivative with respect to B, therefore it's the velocity of B, and because it's of a point with respect to a point which is fixed in B, therefore it's the velocity of P. Okay, very clear. So we're retaining the second term as it is. Okay, now if you look at VPI, now you look at the first two terms, this particular term with this, then you are seeing that it is nothing but the velocity of P in B, and therefore you're just having this, introducing this particular concept of what I started off by saying, that at a given instant of time where you're interested in the motion, you're saying wherever P is, I'm choosing that material point of B, which is fixed with B, as PB. Okay, so once I have that, then you see that that is the velocity PB of I. Okay, so it looks much simpler, in fact, this particular thing. So that's the velocity of P in B and the velocity of PB in I. But PB is a much less complicated point to deal with because it's fixed in B. If you know the motion of B in I, it's much easier to get, as you see from the top equation. Okay, so the velocity of PB in I, of course, is those two terms which you left out, namely your O prime in I and the cross product term, these two. So in other words, the first and the last term you can recognize is nothing but the velocity of a fixed point on B, at which instantaneously that point P was there, and therefore you have now a formula where you can just add two velocities in order to get the velocity of P, which looked very complicated from I. It looked very simple from B itself but complicated from I. But now all that you have to do is to add these two velocities, and you will see that you will require this particular formula for quite a few of the problems that you're going to solve on Wednesday. So instantaneous, to tell in words what this very simple looking equation means, but very powerful and very useful for a lot of problems. All that it is saying is that the instantaneous velocity of an arbitrary point moving with respect to a rigid body P in a frame of reference in which we know the motion of B, namely I, that so if you want V of P in I, all that you have to do is to add up two velocities. One of those velocities is the velocity of P in B of the point which is moving on the body, and therefore its motion with respect to B. And the second one is of a velocity of an imaginary point, which is the material point at that particular instant that you are tracking or interested in. And many a times you can do that in a very generic sense, and therefore this is not something that is going to be of value for just a particular instant of time, but it can be extended in a generic choice to pretty much a duration of time that you're interested in a particular phase of motion. So velocity, the term that you're adding is the velocity in frame of reference I of that point PB, which is fixed in the frame of reference B, but coincident with that particular point P instantaneously. Okay, so that's as far as the simpler case of velocity is concerned, but just one more derivative with respect to time, with respect to frame I, and we can go from velocity to acceleration, which is what we will do in this particular slide. Again, tracking that same point P, which is moving in B and therefore also moving in I, and we want to get from one to the other. So if the point P is fixed in the frame of reference B, which it is not, by the way. So if it were fixed, then we know the formula. In fact, we revised that today. We had derived that earlier class, but now we are just whatever we saw in the beginning of today's class, we are just putting that. We saw that in fact the only difference from the angular velocity to the angular acceleration term is essentially this additional term that you have of the omega coming into picture as well, okay, which is of course what we called as a centripetal like acceleration involving an omega squared r. Now but we know that in reality, and this way the problem definition is for us right now, P is not fixed in B, it is moving in B. So we want to bring in that particular complication there, which is what you see in this particular equation. So it's just an extension of what we did with the velocities. You just have to take the derivative once more, and then you end up with this particular equation that you see over here. Okay. Now the acceleration of P in I therefore can be thought of as composed of three parts to it. Okay, velocity was much simpler. So just like remember, angular velocities are additive, but angular accelerations are not additive. Same thing for this point which is moving on a body. The velocities are additive, okay, but the accelerations are not additive because it involves a third term, okay, which is a non-zero term. A third term is also involved. So in other words, if you're going for the velocity of P in I, all that you needed is velocity of P in B and velocity of PB in I. But now we are not talking of velocities, you're talking of acceleration. So you still have those two terms, but you have a third term as well. And that third term is essentially a 2 omega cross V. Now, if you look at this is, what kind of term is this? Anybody? Because we have visited a similar kind of a term in a particular coordinate system earlier. See, accelerations are all second time derivatives with respect to time, right? But if you look at angular velocity, what kind of a derivative is it? It's a first derivative, right? But you cannot actually go from a rotation vector to that, but you know that it's per unit time, right? Similarly, this is also per unit time. So both are somewhat like first derivatives. Yeah, Gracie?
I was just,
Yeah. Okay. Anybody?
Is it the centripetal acceleration?
Centripetal, remember, had two omegas and an r, right? Here there's only one omega and a v.
Would be the Coriolis.
Yeah. So that's the other thing, right? So remember that the one that we were talking about, which involves a kind of a coupling between translation and rotation, that is your Coriolis. Okay. Whereas centripetal will be there even when there is no translation. All you need is rotation. So whenever there is rotation, you will have the centripetal, but and it has to be taken care of by an actual physical entity. How it is being applied could be a tension in a cord, the friction, the gravity. We saw many examples of that. Okay, but for this Coriolis, you need to have both kinds of motion. One is the translational motion. The other is the angular motion that you have. Only when both of them are non-zero, and you of course cannot have them parallel to each other, then you will have this third term complicating this particular equation. Okay, but it's not a whole lot complicated because we have substituted for those accelerations to get into the familiar territory how we were calculating velocity as sum of two velocities. You just have to make a correction as far as acceleration is concerned with a third term that you see here, twice omega cross v. And what are those angular velocities of interest? Of course, there are only two frames that we are interested in, B and I. So it's of B and I. So quite direct that you can see that. The other, of course, is the velocity that you're familiar with, because you know how P is moving on the body B itself, but we don't know how it is moving with respect to I. So that known quantity is what we are taking the velocity of and crossing these two entities. Okay. Now, so that's as far as the mathematics is concerned, just breaking it up into words or explaining the same thing in words. So you're looking at the instantaneous acceleration at a given instant in time t, as is for any variable that, in fact, when we are looking at as functions of time, we are looking at its value at a given instant in time. Of what are we interested in instantaneously? Of the acceleration of p in a inertial frame of reference or any other frame of reference in which we know the body's motion, right? So in this case, we have chosen that to be I. So what is it made out of? It's made out of three components, okay? So the third component is, as we recognize, the Coriolis acceleration, which is what is making it different from the velocity formula. But the first two are very similar. One is the acceleration of p in the frame B itself. Though we are interested in p in I, the simpler thing is p in B, which we know, and therefore that is the first thing. And to that, you are adding the velocity of a fictitious point, an imaginary point, which is the material point at which p is there at a given instant of time. So you're tracking that point, and therefore its acceleration in I, of course, of that fixed point in B, because if it's fixed in B, its acceleration with respect to B is 0. Okay, so it's of PB with respect to I, and that's of course coincident with P instantaneously. Any questions on this so far? Okay, so you will see that you will very frequently use this for the next few homeworks, both the acceleration formula as well as the velocity formula on the previous slide, which is why you will see that even for simple problems it becomes handy, but as you go to more and more complex problems, the power of this particular simple derivation you will see really helping us quite a bit. Okay, so with that we have completed that particular topic. We get on to the concept of orientation angles. So because remember that when you're talking about a particular position of a rigid body, we should not only give its location of a particular point on it, usually the center of mass, but we also have to specify its orientation at a given instant in time. How is it oriented? So for same two situations, two particular entities might be at the same location in terms of their center of mass, but their orientations could be quite different, and that makes a huge difference in terms of how the motion is going to ensue, especially when control surfaces are involved, for example, in an aircraft, etc. The initial position or initial orientation are equally important, and therefore we need to understand some things about the orientation angles. Okay, And as I've been saying once in a while, without proving that in that way, it's easy to deal with velocities, accelerations, positions, even angular velocities and angular accelerations, but this guy is the most difficult to handle, which is why we are visiting this last. Remember that compared to just like in translation, we had three quantities, which is position, velocity, acceleration, related to each other by time derivatives. First time derivative, second time derivative with respect to a particular frame of reference. So we moved from the simplest, which is position, then we went to velocity, then we went to acceleration as far as translation is concerned. But in rotation, we have already introduced angular velocity concept. We have already introduced angular acceleration, not only conceptually, but even for derivations and other things. We have seen that. But now, finally, we are getting into orientation angle because it's such a complicated thing to deal with. Okay, but we will, at the end of this episode, we will look at what we are looking at in terms of the orientation angle. If those angles were very small, then things become very similar to what you're dealing with position vector to velocity to acceleration. The fact that these can be large in the sense that you're not talking of angles which are, let's say, about 0.1 radians, about 5 to 6 degrees, etc., to just as a thumb rule. You're looking at much larger changes, either in the pitch of the aircraft, or in the rolling of the aircraft, or in the yawing of the aircraft. You typically deal with fairly large angles, which means that it's not of the order of, let's say, 0.1 radians, but much more than that. When you're dealing with that, the orientation angles is a little more difficult to deal with. Okay, but we have ways of doing that. That have been very well established over a long period of time, which is why space dynamics as well as aircraft dynamics have been done to a large extent, and even before actually building the aircraft, a lot of these things happen at the design stage, both preliminary as well as detailed. Now, we know that in terms of the degrees of freedom, just like the translational degrees of freedom are 3 in number along the 3 different axes for general 3D motion. Of course, for planar motion it becomes just 2. Similarly, as far as the rotation is concerned, it also has 3 degrees of freedom about the rotation about those 3 axes. So obviously you need to have 3 angles, and so therefore, but there is a catch to it, that the rigid bodies, let's say B, and you have another frame A. So far, most of the course I was calling A as the frame of fixed to the aircraft, but now for the next few slides, I will call A as the frame with respect to which we are studying the motion, and B is the body whose motion we are interested in. So if you're looking at aircraft as an example, then B would be your aircraft hereafter for the remaining slides, and A would be the frame with respect to which we are looking at its motion. So pardon me for this difference in notation, but essentially this is what I already had in the slides, and I didn't want to make all of the changes that because they are in the pictures and figures as well. Okay, so we are interested in just 2 frames. One is B, one is A, and the main motion we are talking about is of B with respect to A. But in the general case, A could also be moving, because, and it could even be accelerating and rotating itself, because we are not dealing with kinetics as yet. We are essentially looking at kinematics, which is just the description of motion. So it doesn't matter whether A is inertial or non-inertial. Okay. Now, the main reason for the difficulty compared to position vector, velocity, acceleration, angular velocity and angular acceleration of this particular quantity, namely the orientation, is the fact that it cannot be represented as a vector. Okay, but nonetheless it can be represented in terms of 3 angles, because there's the 3 degrees of freedom that you have in rotation in addition to the 3 in translation. Okay, so now since we have 2 frames of reference, which is what we introduced to start with, we introduced 3 coordinate systems, let's say Cartesian coordinate systems, and to those Cartesian coordinate systems we tangentially introduced 3 unit vectors each, and like before, all the unit vectors are hatted to say that their magnitudes are equal to 1, and we will consider orthogonal system, A1, A2, A3 are mutually perpendicular to each other. Similarly, amongst B1, B2, B3, they are also mutually perpendicular with respect to each other. But between the two, they can make any arbitrary angles, and we want to go from one frame to the other frame. And some of these things you might be very familiar with from a simple 2D example or a 1D example. We just want to extend that to 3D, and some of you might be familiar with those 3D examples as well, but just bear with me, because we want to introduce those concepts which are very, very important in understanding rigid body dynamics as a whole, and in particular aircraft dynamics, even if you're treating the aircraft as a rigid body. So we are going to start with the frame fixed to A, and we want to get to the frame fixed to B. Okay, so these are aligned with A1, A2, A3 is aligned with A, B1, B2, B3 hatted, of course, all 6 of them aligned with the frame B. Okay, so when we want to do that, we want to take the fact that there are 3 angles that are involved. Of course, none of them are about the same direction. I cannot say I roll by 10 degrees and then again I roll by 15 degrees. It doesn't make a difference. I would have as well told I roll by 25 degrees, because if nothing is happening in between, it doesn't matter. Okay, so we are looking at 3 different kinds of rotations that are involved in order to go from the A system to the B system. So that now once you do those 3 rotations appropriately and in an appropriate order, which is what we will see, that order actually matters. Okay, to give you a very simple example, you don't even need 3 rotations. Suppose you had 2 aircraft which were kind of having their body fixed frames parallel to each other to start with, and you see that we typically introduce coordinate systems along the length of the aircraft, which is X, going towards the nose. Then you have one which is going towards the starboard, which is the right, which is what you call as the y-axis. And since I cross j has to be positive, your k is downwards. Okay, so your k hat is downwards. So I hat towards the nose, j hat towards the starboard, and k hat which is downward. Okay, so all rotations also will be positive about those axes. So if I wanted positive roll, then it has to be along the positive x-axis, which means that the roll this way, which means the rolling towards the right. Okay, similarly, if you're looking at yawing, which has to be about the z-axis, it has to be positive in this direction, which is again yawing to the right. So it's very easy to remember, both rolling to the right as well as yawing to the right are considered to be positive, okay, according to our sign convention. Doesn't matter, you can always use a different sign convention, but you just have to be consistent within this. And most books use this, so it's good for us to familiarize with this convention so that we are not inventing our own convention and unnecessarily complicating an already complex problem, right? So those are 2 rotations. The third one is the pitch, okay, which is about the y-axis, and therefore you see that it has to be positive in this way, because the positive y is towards the starboard, which is towards the right, which means that the rotation has to be such that the nose up. So you have a nose up pitch, which is considered to be positive, whereas a nose down pitch is considered to be negative. Okay, so this is as far as the convention is concerned. Now, the reason why I started describing is I wanted to say that the sequence matters, and you don't need to go as far as 3 angles, just 2 angles, you will see that the sequence matters. Now, let's say we are going to just have, let's say, yaw and pitch. Okay, so we want to make things very clear. Let's go for large values. Let's say 90-degree roll and a 90-degree pitch. Usually along with roll you will have yaw, but let's not bring in that complication. It's only from the point of view of theoretically understanding why sequence is important. Okay, so now in this particular case, let's say I'm going to do the pitch first and then the roll. Okay, so I'm going to pitch first, and pitch, pitch up is positive, so I'm going to pitch up by 90 degrees. Okay, so I've reached this. Then I want to roll it by 90 degrees, which means I have to roll towards the right. Okay, so which means it has rolled. So this is the final position after both those motions. Now I want to just reverse the sequence. So in this particular aircraft, I wanted to roll first. Okay, so I want to roll first. So once again, the positive will be towards the starboard, so it has rolled this way, right? Now I want it to pitch by 90 degrees, which will once again be nose up. So which means this is the position I end up with. So you very clearly you see that what you have ended up with two entirely different orientations. So it's not just those 2 angles, specifying those 2 angles how many degrees in roll, how many degrees in the pitch, or how many degrees in yaw, but you also have to say in what particular order, because remember that the way I was doing it is not with respect to a ground fixed frame, but with respect to a frame which is fixed with respect to the body, because that's what is counterintuitive to the intuitive to the pilot, that everything is with respect to the body that you're essentially doing. Okay, so it's the new position after the first thing, let's say the 90-degree pitch. It's remember that your B axis have changed, at least two of them have changed. Okay, so and with respect to that only we are going to roll. I'm not going to say I was this way, so this is only roll, so do the same thing over here. That's not going to be acceptable, right? So with respect to the new frame of reference that you have to now roll, so these are all body fixed frames with respect to which you call these entities pitch, yaw, roll, etc., right? So we have to sequentially rotate, and there are three angles involved, and those three angles are about three different axes, and then you eventually go from one to the other. But in doing so, if you're doing it in a sequence, you already see that going from one to the other in three steps, after you have taken the first step, already you have changed the orientation of B's with respect to A, right? So which means that I have to introduce two intermediate frames before I get to the third frame, which is eventually B. Okay, so if you want to have all three, yaw, pitch and roll, you have to start with your inertial frame of reference, align your body with respect to that. Now you include those three rotations about three axes. So one you are going to do about one particular axis, that is going to, the starting one is always going to be very simple because it's these two are aligned with each other. But the next two are going to be intermediate ones that you have to be a little careful about, and we will call those two intermediate frames because they are also body fixed. Instead of B, we will call them as B prime and B double prime. And so you go from A to B prime, then you go to B double prime, eventually you go to B. Okay, these three rotations that you are going to talk about. And don't confuse with the primes as derivative with respect to S, etc. We are talking of frames, and obviously that's not what we are talking about, just a notation that we are using. I would personally prefer like a star or something to avoid the confusion, but I already have the slides with the primes, so I just want to make you aware of that particular notation. You don't see it yet on this particular slide. So what it implies is that the orientation can always be specified in terms of three angles, but it's not a vector. Okay, so even though many other quantities which can be specified as in terms of three entities can typically be expressed as those three angles. For example, if I call the roll as phi, the pitch as theta, and the yaw as xi, then in terms of phi, theta and xi, I might be tempted to introduce a vector with corresponding unit vectors, but it doesn't work that way, and we will see why it doesn't work that way. Okay, continuing with what we were talking about, there are multiple ways to define the orientation with respect to three angles. So just so that we are all on the same page, we need to have some kind of a convention going in place, and which is what we will try to look at it. Okay, so using rigid body, which we will see in the next slide, there is a way of defining the three angles. Okay, so what we call as the space angles, and which is what we have been just talking about, the roll angle, the pitch angle, the yaw angle. Okay, so that is one way in which you could do it. So as we said, there's no unique way, there are other ways of doing it. A second very common way of doing this is to use various sequences in the three different axes, and which we will also see, and it could be simplified with, instead of three axes, just two axes, but it unnecessarily introduces certain complications, so we will not look at that from that perspective, but we will see that that is also a possibility. Then in terms of singularities, so especially if you're using three angles, there is a danger, or in fact at certain angles you will end up with singularities, and we will describe mathematically what that singularity actually means when we reach that stage, so bear with me until then. Okay, but if we restrict the angles, because this singularity is occurring at a particular angle of some of the rotations, so then if we can avoid that, or we can have some way of bypassing that, then we can make sure that we can avoid the issue of singularity, and therefore mathematically the problem becomes tractable. And again, a lot of work has been done over more than a century with respect to this, even work prior to aircraft dynamics in terms of general rigid body dynamics. Okay, but in this particular course, which means just this week, today and in the lectures and the Wednesday homeworks, we are looking at a particular sequence instead of confusing with all kinds of sequences. Already we demonstrated that in the simple case where we had just 2 rotations, the sequence mattered. Okay, so you can obviously understand when you have 3 rotations, the sequence is going to matter. But you will see that most books and most research papers will follow this particular convention. Most pilots also do, that you have this particular sequence in which the rotations are talked about the third axis, the second axis, and the first axis, which is akin to B3, B2, B1, but we are essentially talking about intermediate frames as well, which is the prime and the double prime that I talked about. We will shortly specify that. But in terms of the what we understand as the angle, you see that this is fairly straightforward. The third axis is nothing but your z axis, the second is nothing but your y axis, and the first is the x axis, because that's the order, right? We typically say x, y, z, so b1, b2, b3. But we are doing it in this particular order, 3, 2, 1, as a convention. So there's nothing sacrosanct about this. So don't think of this as something great and anything else is very difficult to achieve, or no, it's not that. Just that all of us want to be on the same page, so we accept a particular convention and stick to that. That's all that there is. So we don't want to unnecessarily, different people taking different sequences will unnecessarily result in totally different solutions to the same problem, which is not acceptable, which is why we choose this. Okay. Now, the third direction, remember, is the z-axis, which means the angle that we are talking about in 3 is yaw. Okay. So this is y for yaw. The second one is second direction, which is essentially going from the port to the starboard along the span of the wing, which is essentially your pitch. So y for yaw, p for pitch. Then you're coming to the last one, which is 1. The axis 1 is along the length of the aircraft towards the nose, and this is essentially what we call as roll. Okay, so YPR, which is notation very something which we in IISc find it easy to remember, because the closest railway station to IISc is Yeshwantpur, and its code is YPR. So it's a mnemonic for some of us to remember this particular sequence, but it's a fairly straightforward thing to look at. It's a reverse order. Instead of the typical ascending order of 1, 2, 3 numbers, you're looking at a descending order, 3, 2, 1, and you have to recognize, of course, 3 is yaw, 2 is pitch, and 1 is roll. Okay, so these are the 3 angles that we are talking about. So if you look at it, are you better at drawing aircraft? My drawing sucks, so that's why. So can you just draw a plan of an aircraft? It's the plan of an aircraft. Yeah. Just the plan from seeing from the top. Similarly, draw a side view as well as the frontal view. Okay, so we will see how the work goes towards the end. In the meantime, let me continue. Okay, so now, as I said, this is whatever we are going to do here is valid for any rigid body, but we are going to be talking about the aircraft because it's an AE course, AE2220. We want to see what is the takeaway, what's the takeaway for the next course you will see in the same sequence, and therefore we need to be prepared for that. So it becomes, that's why this is a prerequisite for some of the other courses. Okay, so now what happens in aircraft flight mechanics, 3 to 1 is what we want to look at. So the second one, I want the side view. Yeah, side view, and the last one is the frontal view. So let's see what we have. So same thing, we have talked about body B and body A. Only thing I'm doing now is to, instead of calling it body B, I'm calling it an aircraft to make the example a little more concrete, right? So aircraft and the frame A with respect to which the motion was taking place, I'm going to call it an earth fixed frame, which is A1, A2, A3 hats are fixed in that particular coordinate system, okay? So initially, let's say both these are aligned with each other. In other words, your B1 hat is equal to A1 hat, B2 hat is equal to A2 hat, and your B3 hat is equal to A3 hat, okay? So now one by one we want to introduce those three rotations. We already agreed on a particular convention. It is going to be Yeshwantpur or YPR, which is yaw, pitch and roll, that is 3, 2 and 1. So therefore we first have to rotate about this. Once we rotate about this, these two are going to change because of the rotation, okay? So instead of B1 hat and B2 hat, we are going to have B1 hat prime and B2 hat prime, okay? Then when we do the pitch, it has to be obviously about the second axis, first 3, then 2. So when we do about the 2, we are not going to do about B2 hat, but about B2 prime hat, okay? Similarly, when eventually the last one that we are going to do is the roll, and we are going to do the B1 hat, it's not about B1 hat, but about B1 hat double prime, okay? So that's all that we want to see. Oh, that's far more beautiful than what I would have done. The last one is the front, as you see from the front of the aircraft.
Oh.
Yeah. Okay, so now, so that's essentially what we are going to do, okay? So we have those two, the starting frame and the starting frame and the end frame, but in between we have two rotations, totally 3 rotations. So we are not going to go directly from this to this. We are going to introduce two intermediate frames, as I said. One is B1 prime hat, then all the BIs, so BI hat, and then with a prime, and then with a double prime. So those are intermediate frames, and then we will see how to get to that, okay? So once he's done with that, I'll mark them on the slide, okay? And those, yeah, yes.
So to do this, so if you're taking the angular velocity of the pitch of the aircraft, you would put B1.
Thanks.
But in relation to Earth is the A1. But if you're trying to do the angular acceleration, say yaw again, it would be B prime off the aircraft. It would be A prime.
No, see, this is the initial position, okay, and this is the final position, okay. So you're going from the initial position to the final position. You don't do it in one single step. You're going to do it in 3 steps because 3 angles are involved, okay. So just to make things a little more clearer in our mind, we are saying that I'm not going from A to B. I'm taking 3 baby steps in doing that. First going from A to B prime, then from B prime to B double prime, and then from B double prime to B, okay. So in reality, that's not how the aircraft would perform it, but from our own imagination perspective, just to see the relationship between 2 arbitrary orientations, I just want to bring these 3 steps so that you are very clear in your mind as to what has happened, okay. Okay, so now let's utilize this and remember the systems that we talked about. One is, of course, your along the length of the aircraft, which we refer to as B1 hat, and along the starboard, which is along parallel to the span but towards the right of the aircraft, which we will call as B2, and typically these are done from the center of mass of the aircraft. So this is your B2 hat, right? Okay, so now B3 hat, of course, is going into the board. So let me just put it as a cross because it's just a plan. So that's your B3 hat. Okay, now to start with, so this is remember that the sequence that we want is this 3, 2, 1, that is Z, Y, X, which means that yaw first, then pitch, and then roll. Okay, so now if you want to yaw, so obviously the rotation is happening about B3. Okay, So which means that this is positive, okay, and that positive means that you're going to have a new set which is different from the previous one by your angle xi. Is there another pen which writes better? Marker? Yeah, thanks. Okay, so you see that the first angle that we are going to have is yaw. Okay, and this is happening about the B3 axis. Okay, and this is the positive direction of this, right? So that's your yaw. Okay, so once it has happened, now you have B3 remaining the same with the new system that we have, which we are going to call as the B prime. So we have moved from, started from A and we have gone first to B prime, because I'm calling it starting with A because your initial thing, everything was aligned, both are aligned. So B1 was A1, B2 was A2 and B3 was A3 when there was this at the start of the motion, right? Now once this rotation has taken place, still your B3 remains the same. So you've gone from A, when you've gone from A to B prime, so initially your A and B was aligned with this, but B is changing, okay, B is transforming, okay. So now you see that the new frame that you have, the B3 prime is also going to be the same, right? So because, again hatted because these are all unit vectors. So now you see, because the rotation is happening about the z-axis, which is why you see that B3 and B3 prime are same as each other. Only change has happened in your B1 and B2, right, which have become now B1 hat prime and B2 hat prime. This is also, this angle is also same as that, which is your xi, which is the yaw angle that you see, right? So that's as far as the first one is concerned, that is taken care of, right? So we know that we have gone from the A frame to the B prime frame by just the yaw alone. The next one, we want to go from B prime to B double prime. That is going to involve a pitch. So this involved a xi. Now there's another transformation that we want, which we will call as theta, which is the pitch angle. Okay, so this is yaw, this is pitch, which will also not take us to the final orientation that we want. It will take us to an intermediate frame, which we are going to call as B double prime. And as always, we have been circling our frames of reference or rigid bodies to distinguish the notation from points and other things, right? So then finally we will do another rotation, but let's first talk about the pitch, going from B prime to B double prime. Okay, which of these two figures do you think it's easier for me to demonstrate that, the pitch? No, good. Yeah. So you now are starting with that primed system, that is essentially this, right? So you're having a B1 hat primed and you're having a B3 hat prime in this particular side view that you're seeing. Okay, what about the B2 hat? Is it going to be coming out of the board or into the board? Yeah. So essentially it's a point, right? So that is what you have over there, which is your B2 prime, right? So now we want to have a pitch, and we have said that whereas yaw and roll towards the right is positive, pitch up, which is nose up rather, is essentially positive. Okay, so if it's going to be nose up, then you're going to have a new angle over there. and we are denoting the, I've not talked about that, we are denoting that by the Greek letter theta, right? So that angle nose up positive is theta, so this is also theta, okay? And what you have got to now is a second intermediate frame, B double prime, and therefore unit vectors associated with it will all be lowercase b hats with the double prime, right? So this B1 prime has now become B1 double prime, okay? Similarly, your B3 prime has now become B3 double prime, okay? So the difference between B and B prime was in yaw, and only two of the unit vectors changed, namely your B1 to B1 prime and your B2 to B2 prime. The third one remained the same. Similarly, here also one of them remains the same, which is your B2 double prime, right? So B2 prime and B2 double prime are one and the same, right? So now we have done 2 steps of yaw and pitch. The third thing that we would like to do is, of course, your roll. So we want to go from B double prime to the final orientation that we wanted, which is your B. Okay. So these are purely mathematical, figurative, and not necessarily the practical way in which the aircraft does it. What we are interested in going from A to B in terms of the actual maneuvers, etc., it could be, and again, it may not be unique as well, but eventually we want to go from A to B, okay? But purely from a schematic point of view or mathematical point of view, we want to introduce these two intermediate things, so it's easy for us to appreciate how we are doing it, okay? So now that's pitch, and then of course finally you're looking at roll. Okay, so that roll is defined or denoted by phi, okay, lowercase phi. So all these are lowercase xi, lowercase theta, and lowercase phi. Okay, so yaw, pitch, and roll. So now we have this third figure, which is the frontal view of the aircraft. And so we start with a particular thing. Remember that already we have gone from A to B prime, and we have gone from B to B double prime. Now we have to get to B. So we start here in this case with B double prime. Okay. So if this is you're seeing from the front, then you see that this is the right side, which is the right wing, which is your starboard. So which means that you would have, in this particular direction, your B2 hat double prime, right? And you would have the downward direction, you would have your B3 hat double prime, okay? What about B1? Oh, wait, what did I do? That's B2, this is B3. So going from 2 to 3, right, yeah. So you have 2 cross 3, so it's coming out, right? So you're seeing this aircraft from the front, which means that the nose is what you're looking at, right? So your B1 hat is in that particular direction, which means that you would denote this with a point over there instead of a cross, right? The way you see it, this particular picture. Now you're looking at this particular angle roll, which is positive in this particular direction. So you would end up with the final value of that unit vector, which is, instead of B2 double prime, it just becomes B2, and this will become your B3, and that angle that by which it is rotating is your phi, right, which is the roll angle. Okay, and of course your B1 double prime is equal to B1 because the rotation is happening above that, right? So it's fairly simple. Single rotations you're already familiar with, but here just we are breaking up this complex orientation change into 3 parts, each of which you understand very well. So you're essentially going first with yaw, where you're not changing the third direction, which is why we say it's a rotation about 3. Then you're doing the change about y, the rotation about 2, which is why we say 3, 2 and 1. The last one is about 1, which is why that remains the same. Okay. So in the first case, the third axis remains the same. Second case, the second axis remains the same. In the last case, the first axis remains the same. The other two change by that particular angle of xi, theta and phi, which are nothing but yaw, pitch and roll. Okay, and whatever we have shown here are positive by convention, but in general you could have negative values for these as well, and that will be opposite in sign. Okay. Yeah, please.
Are they Euler angles?
No. So this is one way of looking at the same. Euler angles is an alternate way of looking at it. Okay, but you can really correlate the two.
Both are almost looking similar. Here it is U312.
Yeah, exactly.
Here you are doing
Exactly.
2-1.
That's right. So this is a convention that we follow typically in aircraft dynamics. But Euler angles is a concept which is generic for all rigid body rotations. Okay. So what you said is right, that a particular sequence. So I just didn't want to confuse by bringing that up. So we will look at some aspects of that little later. So now, so essentially 3 angles were involved, which was yaw, pitch and roll, about those 3 axes that we are talking about, z, y and x. Okay, and the notations, these are again standardized notations for xi, theta and phi is used in pretty much most aircraft dynamics books, so just be familiar with that. Okay, now you consider these 3 angles, xi, theta and phi, yaw, pitch and roll, representing the rigid body rotations about the third axis, which was A3. Then you had to look do the rotation about B2 prime and then about B1 double prime. Okay, so orientation from Earth frame of reference A eventually to the final orientation that you want for your aircraft or the rigid body B, which is the frame B. Okay, so now yaw is to rotate by an angle xi that we saw over here about the Earth's axis, which is A3, and you get an intermediate frame of reference that you see over here, B1 prime and B2 prime. Of course, B3 prime remains the same as A3. Then the second thing that we did was pitch, which we see in green over here. So you rotated about theta, about the new intermediary axis that you got, which is your B prime, which is in particular B2 prime, which is why that remained the same, and you got moved to the second intermediate frame. Instead of B prime, you now have a B double prime. Okay, and the last one, which you see in blue and black over here, which is what you see over here, which the angle is phi. You have moved from one frame, which is B double prime, to the final frame of interest, which is B, which is the aircraft fixed rigid body frame of reference. Okay, so now we're looking at in terms of all of this so far, we looked at it from a schematic to try to draw. Even though we have been dealing with unit vectors, we are only showing that geometrically over here, but we want to look at the algebra behind it, the linear algebra behind it. What do these transformations mean? Of course, some vector equations we have already written, which is the very simple ones, which is all equals, because the rotation was happening about that. Similarly over here and similarly over here. But we know that even the other two can be related. Your B1 hat, B1 prime hat, etc. can be related, which is what we are going to do in the simple vector transformations that are required over here, which will of course involve the cosines and sines of the angles in each one of those rotations. So once again, we are not going to directly jump from the Earth fix to the final orientation. We are going to go in those steps. What was the first step we took? We wanted to go from the A system to the prime system, B prime system, by an angle xi, taking the rotation about the third axis, which is what you see, that angle was xi, okay, the yaw angle. So it takes the aircraft from the Earth fixed frame of reference A to the intermediary frame of reference B prime, which we denoted by the unit vectors B1 prime, B2 prime and B3 prime. It's very straightforward and simple. that all that you're going to go from this, remember all these are unit vectors, which is why they all already have hats. But if you want to go to B1 prime, you can take a distance cos xi along A1 hat, and then you have to take a vertical distance over here along your A2 hat in order to reach this, which is going to be sin xi. Okay, so you go cos xi about along A1 hat, and you go a distance sin xi parallel to A2 hat, and when you do that, you end up with B1 hat, which is what all that this is saying. It's a sum of two terms. One is you're going a distance cos xi or parallel to A1 hat, that is the horizontal direction, and you're going another vector. So it's a vector addition that you're essentially looking at. This vector B1 hat can be thought of as a sum of two vectors, one which is parallel to A1 hat, which is having a magnitude cosine xi, and one which is parallel to A2 hat, which is having magnitude which is sin xi, because it's the opposite side there. Okay, very clear. Okay, so again, similarly, if you want to get to B2 prime, all that you have to do is again take those two steps. First you take cos xi, so because this angle is also xi, so you're taking a distance. This whole thing is a size of 1 magnitude. This is also 1, but you're not going the whole distance 1, you're essentially going only up to here, which is cosine xi is the magnitude, but parallel to A2 hat, which gives you the second term over here. Okay, then you want to, after having gone this distance, now you want to go horizontal direction. You want to get to this, which is opposite side, which is your sin xi, which is how you get this, but it's in the negative A1 hat direction. Okay, not unlike the first one. So one term becomes negative over here. Okay, so very clear. And the last one, of course, is the rotation is happening about that axis, and therefore those two are equal to each other, which you see B3 prime is equal to A3. Okay, now of course you can invert those relationships, very easy, same thing. Essentially you are going to have this set of equations. Anyway, you have the slides, so I'm not going to discuss this specifically. Okay, now the same thing, this is written as 3 separate scalar equations or 3 separate vector equations. I can write it as a single equation in a form of a matrix, right? So I'm just going to see that the right hand side is all in terms of A1, A2 and A3. So I'm going to put them all into a column matrix, A1 hat, A2 hat and A3 hat. And the left hand side is nothing but B1 hat, B2 hat, B3 hat. I'm just going to get the coefficients of each. And you see the first equation doesn't have a A3 term, second also doesn't have an A3 term. So you see those two zeros. And the last one, of course, just trivial, B3 hat equal to A3, and therefore just as a 1 over here, whereas the others are going to have these cosines and sines. So again, something that you're very familiar with from other courses. Okay, then same thing we can do for the going the other way around, from the B system to the A system. If you want to look at it from that perspective, then you from this you can very easily see that the coefficients are going to result in this. Now this is a result you probably some of you are familiar with already, that obviously one is taking you from the A frame to the B prime frame, the other is doing the exact opposite, which is taking you from the B prime to the A. Obviously means that you're going from one orientation, this is just through yaw, right? So you're going from this orientation to a different orientation over here, right? So, and if you want to come, whereas that is one matrix, whereas the other matrix is coming back from this to this, right? So obviously they are inverse of each other. Okay, so which means that if I take the inverse of this 3 by 3 matrix, I should get this particular matrix. But the beauty of this particular kind of matrix, which we will revisit quite a bit once we are have completed this in what is known as a direction cosine matrix, we will see that you actually don't need to take an inverse, which is a difficult thing because you have to calculate determinants, etc. Here all that you see is, if you just visually inspect these two, you will see that one is the transpose of the other. In other words, the rows that you see over there have become the columns over here. You have CS0, you have CS0. Okay, the second row you have minus SC0, here you have minus SC0, right, as a column. So what were rows there have become columns here. Okay, so that's the beauty that you see. But we know that because the things that they are multiplying and what they are resulting in is just interchanged. here you've got B primes in terms of A, and here you're getting A's in terms of B prime. So it's essentially interchange these two, which means that they are inverse of each other, which means that just by transposing I'm able to get to the inverse. This is a special quality of a kind of matrices what we call as unitary matrices, or they're also called as orthonormal matrices, okay, or because they involve orthogonality principle and also a normality because they're all involving unit vectors, okay. So we will revisit that in a formal sense a little later, but for now in the simple case in which you have only the yaw, you have seen this happen. But the same thing holds for the pitch as well as the roll in the next two steps, because here you have just gone from one frame A to a frame B prime, and in the next you're going to go from B prime to B double prime, okay. Any questions on this? I think it's fairly straightforward, right? So this is what we will abbreviate for the rest of the slides that we have for the afternoon as well. We will call it as DCM, referring to direction cosine matrix. Why is it called that way? Because remember that it's relating to entities which are unit vectors, which essentially give you directions. Because their magnitude is always 1, it's only their utility is in terms of specifying directions for you, and they involve cosines and sines, so essentially therefore call it a cosine matrix. And when these angles are 0, you see that all the sine terms will drop off, only the cosine terms will remain, which will become of course unity, and therefore you'll end up with identity matrices for both, okay. So in other words, you're saying that those two sets of unit vectors are going to be the same if there is no yaw, okay. So in this particular case, that is A, the set of unit vectors A and the set of unit vectors you have for B prime are going to be the one and the same. Okay, so next we want to go to the next step, which is the pitch. We finished yaw. So now when you're pitching, you see that this is the thing, and we said that the rotation is happening about B2 prime, which is resulting in a double prime system, but B2 remains the same, okay. In other words, B2 prime and B2 double prime are equal to each other because the rotation is happening about that by an angle theta. So irrespective of what is the value of theta, this is what happens, right? So now you're taking the aircraft to its new intermediary frame of reference, which we have called it as the double primes, which is why we say B1 double prime and B3 double prime over here. So that's what, and it's very similar, just that the term on which the cosines and sines operate and which term is missing, that's going to change, okay. So there B3 was identical, the third direction was identical. Here you're having the second direction identical because the rotation is taking place about that, right. So that is the second rotation. The final rotation that you have is of course the roll that you saw over here in blue and black, and that when you do that, you're going to go from the double prime frame B double prime, big B double prime, to the big B frame, the final orientation of the aircraft or the rigid body. So to get aircraft to its final orientation, and that's once again very similar, it's just that the roles of B1, B2, B3 are going to change, but essentially it's relating those sets of unit vectors, okay. Since you have the slides, you can go back and look at it in detail, but there's nothing big deal over here. It's just doing the same thing about three different sets of axes, one after the other. Okay, now coming to the angular velocity, because so far we have been looking at the orientation, and I already told you that whereas in translational motion you could get to the velocity by taking the time derivative of the position vector, why can't we do that from an angular perspective? Now that we have the orientation angles, can't we just take its time derivative to get to the angular velocity? I already warned you that that is not possible, but we want to see the reason why it's not possible, okay. So now we have these three axes that you see, the roll axis, the pitch axis, and the yaw axis. But in the initial stage, if you introduced x, y, z and your b hat system, we know that it's not about that the rotation is actually taking place. Yes, the first one was true. It was happening about B3. But the next one already is not happening about the B system. It's happening about the prime system. The last rotation is happening about a double prime system. Okay. So all these three are going to be quite different from each other. And that's the reason why we will see that you cannot express the angular velocity as a time derivative of the orientation angles expressed in a vectorial form right away. Okay, so finite rotation is not commutative, again, that we saw, right? So these two, one was pitching first and then rolling, the other was rolling first and then pitching. You saw that the orientation turned out to be quite different, the final orientation. Once you involve the yaw as well, obviously things are going to be even more complicated. So in other words, mathematically the way of stating that is that your finite rotations are not commutative. We will see a special case once we are done with this of infinitesimal rotations where you can express things as a vector, and there the sequence will not matter because of that particular approximation of small angles that you have. But otherwise sequence does matter, which is why we have this convention of 3-2-1, yaw, pitch and roll. So common to write the angular velocity as a vector, which it is. In fact, the angular velocity of the body B in the frame A, where B could be the aircraft frame and the A could be the earth fixed frame or an inertial frame of reference for all practical purposes. So it has three measure numbers because we're dealing with a 3D space, and that's what you have as P, Q and R, your the three angles that you have, which is the roll rate, which is you have your pitch rate, and you have your the yaw rate. Okay, but these three, I should warn you, and we will prove that as well, are not directly equal to those angles that we introduced. Namely, for yaw, for example, we introduced the notation xi. So this is not equal to xi dot. Okay, this is not equal to theta dot. Similarly, your P is not equal to phi dot. Okay, it's quite obvious that why this is happening, because of the first fact that these are not in sequential order, and therefore you're seeing that the first rotation is happening about a B system, the second rotation is happening about a prime system, the third one is happening about a double prime system. So you see in all these three cases, it's not the same set of vectors that you're following as far as the rotations are concerned. It's a new body fixed frame that you have to deal with. Okay, it's a body fixed frame, but the body itself is rotating, and therefore the unit vectors have changed. And finally, you have this angular velocity measure numbers. They cannot be integrated individually, just like I said that these cannot be related to the dots of the phi, theta and xi. Similarly, the angular velocity measure numbers you cannot get by integrating your P, Q and R. It's the other way of stating that, because integration and differentiation, remember, are inverse of each other. Okay, so can't be integrated individually to get to the correct orientation angles, but they are related to orientations in a mixed basis, which involves the unprimed B's, the single primed B's and the double primed B's that we introduced here. And therefore, once you bring in the mixed basis, you could do a few things, but things get a whole lot complicated, so there's no point in taking that path. There are other ways in which we will handle this. Okay, so we will do the rest of it after lunch. Bon appetit.